This is a tutorial video about problem 10 from homework 3A that was due on Monday morning, April 12th. I noticed many of you had some trouble with this one, and so I just wanted to take a minute to walk through how to do the problem so you all can reach an understanding of that. So I've copied the problem here, and you may notice that the wavelength is different on your homework. Each of you probably has a different wavelength. The problem-solving strategy should be generally the same. So a ground state hydrogen atom absorbs a photon of light with a wavelength of 93.0 nanometers. What is the final state of the hydrogen atom? So when I look at this problem, the first thing I'm thinking is I'm zeroing in on this absorption of a photon. And the absorption of a photon means there's some sort of electron transition happening. Specifically an absorption, an increase in energy. And when I'm talking about an electron transition and increase in energy, and I want to calculate the energy change, I know I need the Rydberg formula, the one that has multiple n values in it. So that's where I'm going to orient myself to start. So once I'm here, I look and find out what information from the problem I have and what I need. So I see that this says, what is the final state of the hydrogen atom? So that means n final is the variable I'm trying to find. I know k is a constant. N sub I is kind of a tricky one to find because I don't see n sub I listed anywhere here, but I do see this piece of information. I see that it calls the hydrogen a ground state hydrogen. And you may remember that the ground state is the level n equals 1. So that means our initial state is going to be the n equals 1 state. So that just leaves the change in energy. And I don't have a value for energy, but I do have a value for wavelength. And I know that I can get to energy from the wavelength. So there's a formula that we use to convert between those, and that is E equals H times C over lambda. That should allow us to convert from wavelength to energy, give us that last number that we need to solve the problem. And after that, we just need to rearrange this algebraic expression to solve for n sub f. So I'm going to choose to plug in the numbers first and rearrange my algebra later. So the first thing I'm going to do is to solve for the energy. So H is Planck's constant, 6.626 times 10 to the negative 34th. And I believe that is joules times seconds. Yes, joules times seconds. And then C is the speed of light, 2.998 times 10 to the 8th meters per second. So those seconds cancel. And then my wavelength goes on the bottom. And remember that it needs to be in meters, not in nanometers. So I'm going to take my 93.0 nanometers, and I'll just do the conversion right here in the formula. There are 10 to the 9th nanometers in 1 meter. So now the nanometers are gone, and the meters are gone, leaving just joules. Go ahead and calculate that. So we have 6.626, and make sure you use this E button. There's a double capital E above the comma. And when we press that, it gives us a small e here where we can put the negative 34 exponent. It's much more effective to use this button to enter your scientific notation than to multiply by 10 to the negative 34th, because this ensures that we don't get our multiply and divide mixed up. Let's see, so times 2.998 e to the 8th divided by 93 e to the negative 9th. Okay, that gives me 2.136 times 10 to the negative 18th joules. That's going to be my delta E value. And now I'm ready to solve the Rydberg equation. So we've got delta E equals negative K 1 over NF squared minus 1 over NI squared. We'll plug in our value for energy. Plug in our constant for K. So negative K constant is 2.179 times 10 to the negative 18th joules. And then we've got 1 over NF squared, which is unknown, and 1 over 1 squared. Okay, so from this point, we just have to do some algebra to rearrange and solve for n sub f. So the order of operations tells us we want to try and isolate this term. And so we're going to first divide both sides by this k value to move it out of the way. Okay, so divide by negative 2.179, the negative 18th. That gives me negative 0.980. And I'm left with 1 over n sub f squared minus 1. 1 over 1 squared is just 1. So I'm still trying to isolate this term with my variable in it. So now I'm going to move the 1 to the other side. So now I have 0.0197 equals 1 over n sub f squared. Okay, there are two ways we can proceed from this point. We can either take the inverse of both sides and then take the square root, or we can take the square root and then take the inverse. The order doesn't matter. I think I'm going to choose cross multiply because that's easiest for me. So I'm going to write my fraction over 1, and that's going to give me 0.0197 times n sub f squared equals 1. And I can divide both sides by my decimal. Isolate my n sub f. This problem is just going to go all over the place, so hang with me. Okay, so now we've got 1 over, that answer is 50.668. And then we can just take the square root of both sides to find n sub f. So what I'm getting on my calculator, you can see, is 7.118 and so on. It's a long decimal, but we know that n sub f needs to be an integer number, something that's 1 or greater. So we're going to round this to the nearest integer, which is 7. So our n sub I value was 1, and our n sub f value is 7. So even if your wavelength looks a little bit different, the problem-solving process will be the same. Hope this has been helpful, and good luck finishing your homework.